Welcome to the 50th Engineers Newsletter Live program. I'm Jeannie Harshaw from Trane System and Application Engineering Group, and today we'll be discussing chilled water terminal systems. Before we get started, Mick, since you were on the first broadcast, how about a few comments about that first one?
Well, first I have to say, wow. Thank you for being with us for our 50th Engineers Newsletter Live. Since the low-dollar chiller plant in August of 1999, your ideas have really helped us keep this series relevant and applicable. In addition, we greatly appreciate your comments, since they helped us improve our version of Geek TV. Now, in answer to your questions, yes, I was on the first ENL, and yes, all three of the others on today's ENL were born prior to that first broadcast.
Today's program is registered with the American Institute of Architects Continuing Education System and qualifies for Health, Safety, and Welfare credit. AIA members, please provide your member number to your local host before leaving today's session. And credit for attending this program can also be applied toward the LEED Credential Maintenance Program or your Professional Engineer's License. So PEs, please check your state's requirements. Now, in a typical chilled water terminal system, each zone has a dedicated terminal unit that provides cooling or heating to maintain the desired temperature in that zone. All these terminal units are then connected to a common chilled water distribution loop that includes one or more water chillers and pumps. Some types of terminal units may include an outdoor air damper, but typically outdoor air is conditioned and delivered by a separate dedicated outdoor air system. There are several types of equipment that can be categorized as chilled water terminal units. Today, we'll discuss systems that use various styles of fan coils, chilled beams, or radiant cooling. We'll start by discussing these various types of terminal units, then we'll discuss the dedicated outdoor air system, and finally, the chilled water system that serves this type of equipment. Now, there are some aspects of designing and controlling a chilled water terminal system that are similar, regardless of which type of terminal equipment is being used. But there are other aspects which are unique to each one, or just a few, of these equipment types. We'll do our best to point out some of these unique aspects during this program. To cover this subject, we have a guest, Eve London, Trane Product Manager for several terminal products. Eve will be joined later by Trane Applications Engineers John Murphy and Mick Schwedler. So Eve, let's get started by talking about the different types of terminal units.
Thanks, Jeannie. The most common type of terminal unit is the fan coil. A fan coil assembly consists of a chilled water cooling coil, a small fan, and possibly a heating coil. The fan is used to draw and return air from the zone, which then passes through the cooling coil before it's discharged either directly into the zone or through supplied ductwork and diffusers. Some styles of fan coils include an outdoor air damper, but as Jeannie mentioned earlier, typically ventilation is delivered by a dedicated outdoor air system. Fan coils are available in several configurations to suit various building layouts. One of the most common styles is a vertical cabinet. This configuration has a full sheet metal cabinet, so it can be installed within the occupied space. The horizontal concealed unit has no casing because it's usually installed within a ceiling or floor plenum. And a vertical stack unit is designed to be recessed into the wall in a multi-story building. These units are aligned above one another to minimize the cost of installing piping and electrical service. There are also other types of equipment which are similar to the fan coil, such as the blower coil. This unit is specifically designed for ducted applications with higher airflow and static capability, and the classroom unit ventilator, which is designed specifically for school classrooms. It has a more durable cabinet and includes an outdoor air intake that's sized to enable airside economizing. Another similar style of chilled water terminal product is the series fan-powered VAV terminal that's equipped with a chilled water cooling coil on the plenum inlet. Recirculated air from the space is drawn through the cooling coil by the local fan. This cool air then mixes with the conditioned outdoor air that's delivered to the VAV damper by a dedicated outdoor air system. The terminal fan is equipped with an ECM, allowing supply airflow to vary as the space load changes. In most cases, the water supplied to this local cooling coil is controlled to a temperature above the dew point in the space. This avoids moisture in the air from condensing on the coil, so it operates dry and provides only sensible cooling. Of course, you could apply the same approach with a conventional fan coil product by selecting the coil for sensible cooling only. Now let's take a look at various fan motor types typically used in terminal products and review some recent improvements in fan motor technology. Fan coil and other small terminal products have traditionally used permanent split capacitor or PSC motors. These are reasonably cost-effective and efficient when they're larger, say over a half horsepower, and when they run close to synchronous speed. However, most terminal products use much smaller motors and run far from synchronous speed. Many applications require units to operate at multiple speeds. This results in a considerable amount of slip, which creates fan energy losses and is one of the reasons why many manufacturers are considering other motor technologies. Electrically commutated motors are an alternative to PSC motors and are gaining in both acceptance and popularity. These are also known as brushless DC or BLDC motors. For terminal products, we often refer to them as permanent magnet motors or EC motors. Brushless technology extends service life and reduces maintenance of the motor. These motors are well suited for applications requiring speed control over a wide operating range. EC motors have some distinct performance advantages in chilled water terminal products. They have the ability to operate in constant volume or variable air volume applications. In constant volume applications, the motor ramps up or down softly between speeds, and the speed set points such as high, medium, and low can easily be reprogrammed. For example, if high speed is too loud, the high speed setting or RPM can be lowered to minimize sound levels. While this is easy and safe for hydronic units, there are some restrictions on changing speeds with electric heat and DX units to assure reliable operation. In variable speed applications, the high and low speeds are set allowing the motor to run at any RPM within the range. The motor operates at the lowest speed necessary to meet the space load requirements and ramps up or down when the space load changes. This soft ramp capability means fewer audible changes and a substantial decibel reduction in system noise. Another inherent benefit of variable air volume is better dehumidification. Operating at lower speeds for more time delivers colder, drier air to the space, which improves IEQ and comfort. In terms of efficiency, EC motors are much more efficient than PSC motors, especially in smaller sizes. At low speed, it is not uncommon to see motor efficiencies in the 15 to 20% range for PSC motors. EC motors have a technology advantage here because they do not have the same amount of degradation at lower speeds. They can have full load efficiencies of 70% or better and have part load efficiencies that are significantly higher than PSC motors. Later in the program, we will see how motor efficiency translates into energy savings by comparing the power consumption of an EC motor to a PSC motor.
Eve, I'd like to ask a couple questions. In the past, most terminal units had constant airflow. Now with ECMs, the fan coils can operate at variable airflow, which saves fan energy and produces better humidity control. So how is the airflow controlled, and then how is the coil capacity controlled?
Let me walk through that, Mick. Fan coils and other terminal products have traditionally been applied in a single-zone, constant volume system. In this type of system, a temperature sensor in the space is used to vary the cooling capacity in response to changes in the space cooling load. The supply fan delivers a constant quantity of air at all times. A more efficient way to control zone temperature is single-zone variable air volume, or single-zone VAV. This is a high-efficiency system in which the temperature sensor in the space is used to vary the airflow delivered by the supply fan. Cooling capacity is modulated to maintain the discharge air temperature at set point. Let's take a closer look at the system. First, the controller compares the current zone temperature to the active set point. Based on the rate this temperature is changing and any deviation from set point, the controller determines how much cooling or heating to provide to the zone. So far, nothing is different from conventional unit control. What's different is that now the single-zone VAV sequence determines both the fan speed set point and a discharge air set point temperature. Cooling or heating is then controlled to maintain the discharge air temperature at the set point. I'll use this chart to explain. The x-axis is the sensible load in the zone, with design heating load on the far left and design cooling on the far right. When the zone is at design cooling load, the fan operates at maximum speed and cooling capacity is modulated or cycled to maintain the discharge air temperature at the design value for cooling, 55 degrees for example. As the zone cooling load decreases, fan airflow is reduced as needed to maintain the desired temperature in the zone. This is accomplished by varying the speed of the fan through the EC motor. Cooling capacity is then modulated or cycled to maintain the discharge air temperature at this same design set point. Eventually, the zone cooling load decreases to the point where the fan reaches minimum speed. As zone cooling load continues to decrease, the fan continues to operate at this minimum speed, but now the controller gradually resets the discharge air temperature set point upward to avoid overcooling the zone. As this temperature set point increases, eventually no mechanical cooling will be needed, meaning that the cooling valve will reach fully closed. When that happens and the load continues to decrease, the zone temperature begins to drop below its cooling set point into the deadband between cooling and heating set points. Here the fan continues to operate at minimum speed with no cooling or heating, and the zone temperature is just allowed to float within that deadband. Now let's consider what happens when the zone eventually requires heating. When the zone temperature drops to its heating set point, the fan continues to operate at minimum speed and the controller begins to reset the discharge air temperature set point upward even further. Heating capacity is staged or modulated to maintain this discharge air temperature. Eventually, the zone heating load increases to the point where the discharge air temperature reaches a preset maximum limit. As the zone heating load continues to increase, fan speed is again increased, while heating capacity is staged or modulated to maintain the discharge air temperature at this maximum limit. To summarize, let me explain it in a slightly different way. At high cooling loads, the fan speed is modulated to maintain the zone temperature at set point, while cooling capacity is modulated or cycled to maintain the discharge air temperature at set point. At lower cooling loads, once the fan is turned down to minimum speed, it remains at this minimum speed while cooling capacity is modulated or cycled to maintain the zone temperature at set point. Operation is similar on the heating side. At high heating loads, the fan speed is modulated to maintain the zone temperature at set point, while heating capacity is modulated or cycled to maintain the discharge air temperature at the maximum limit. At lower heating loads, the fan operates at minimum speed, while heating capacity is modulated or cycled to maintain the zone temperature at set point. Now this is just some of the basic sequence. There are some nuances depending on whether a two-position or modulating valve is used or the type of heat in the unit such as hot water, steam, or electric. And if electric heat is used, the controls vary a bit depending on whether the heat is staged or has SCR control. Now that we understand EC motor technology and single-zone VAV system control, let's take a look at how this translates into operating cost. Trane has a tool to help model the power consumption of a unit with different motor types. In this example, a 400 CFM fan coil unit with a 3-speed PSC motor is compared to an EC motor with a single-zone VAV control. Both units have the same number of run hours and 11 cents per kilowatt hour is used for the utility rate. The unit with the PSC motor operates at 482 kilowatt hours, while the unit with single-zone VAV control operates at 204 kilowatt hours. This is a 57% reduction in operating costs when compared to the unit with the 3-speed PSC. This is because of the efficiency gains that come from the ability to operate the EC motor at the lowest speed necessary to meet the space load. Now John is going to talk about other types of terminal equipment.
Another style of chilled water terminal unit is the chilled beam. Generally, these are classified as either passive or active. A passive chilled beam consists of a fin and tube cooling coil, usually contained in a housing and suspended from the ceiling like these examples shown here. Chilled water passes through the tubes of the heat exchanger, and warm air from the space naturally rises up to the ceiling, and as this warm air surrounds the chilled beam, it's cooled. This cooled air is now more dense, so it descends back down into the occupied space. This convective air motion allows a passive chill beam to cool a space without the use of a fan. Of course, this motion does not work too well for heating the space, since the warm air just tends to stay up near the ceiling. So typically heating is provided by a separate system, often baseboard heat or in-floor radiant. Now, outdoor air required for ventilation is then delivered by a separate dedicated outdoor air system. And since passive chill beams are not equipped with drain pans or condensate drain lines, the water supplied to them is controlled to a temperature above the dew point in the space. This avoids moisture in the air from condensing on the beams and dripping into the space. So the beams are meant to operate dry and provide only sensible cooling. Dehumidification of the space must then be performed by the dedicated outdoor air system. Active chill beams are similar to passive beams in that they're also typically suspended from or recessed in the ceiling, as shown here. The primary difference is that an active beam contains an integral air supply from a centralized air handling unit. This primary air passes through a series of nozzles, and this local high velocity creates a sort of a wake effect which induces air up from the space and through these cooling coils. This induction process allows an active chill beam to provide significantly more cooling capacity than a same-size passive beam that relies on convection alone. Now, similar to a passive beam, an active beam does not include a local fan, but it does require fan power to cool the space. It relies on a centralized fan to pressurize this chamber so that these nozzles can induce sufficient room airflow across these local coils. Again, since they're typically not equipped with condensate drain lines, the water temperature is controlled so that they'll provide only sensible cooling and stay dry. Now, one clarification here. Some manufacturers offer a drip pan mounted underneath these coils, but still there's no means to drain away that condensate. So this pan is really just a safety precaution. You don't want to operate these coils wet, because then ASHRAE standard 62.1 would require a MERV-rated filter upstream of these coils. Plus, the added pressure drop as the room air passes through that filter and the condensate on this wet coil would then require an even higher pressure in this chamber, which means more fan energy. So the separate primary air system that supplies the active beam nozzles and drives the induction process also must provide the outdoor air needed for ventilation. And it must provide all the dehumidification to control the space dew point and avoid condensation on the beams. We'll discuss these three functions a little bit later in the program. Now, unlike passive beams, active beams can be used for heating. Because of the forced air induction, you can pump warm water through the local coils and heat the space. Now, some beams are available with a 4-pipe configuration, where the coils are circuited to keep the cold water and warm water separate. But as you can see here, this takes some of the tubes away from the cooling circuit. So the cooling capacity of a 4-pipe beam is less than that of a 2-pipe beam, which means you need more beams to offset a given load. To avoid this, some designers use 2-pipe beams with a valve configuration that can direct water from either the chilled water piping or hot water piping. When a zone needs cooling, the diverting valve delivers water from the chilled water supply pipe and then routes it back down into the chilled water return pipe. Then for heating, these same valves just switch to deliver hot water supply to the coil and route it back to the hot water return. Now, other designers will connect the 2-pipe beams to the chilled water piping for cooling only, and then provide heat with a duct-mounted hot water coil in the primary air duct for that zone. When the zone needs heat, the chilled beams are off, so they're just acting as diffusers in this mode, and all the heat's being done in the duct-mounted coil. And then in many cases, heat is provided by a separate system, like a baseboard heat system or radiant. The coils and the two-pipe beams are used for cooling only, while this separate system is used for heating. The final type of chilled water terminal we'll talk about today is the radiant panel. These panels are typically mounted on the ceiling or walls of the room. They do not use air movement through a coil, but rely on radiant heat transfer to cool or heat the occupants in the space. These small tubes carrying chilled water are either embedded in or attached to the back of these panels, creating a cold surface. With radiant heat transfer, you aren't really cooling the air in the room. Heat radiates from the occupants or any other warmer surface to these cooler surfaces of these panels. Of course, these saved panels can also be used for heating by supplying them with warm water instead. Again, to avoid condensation on the cool surface of these panels or tubes, they're supplied with water that's controlled to a temperature above the space dew point. So they provide only sensible cooling. And the separate dedicated air system must provide all the dehumidification. Now, while it might not be entirely accurate to classify this as a terminal unit, another variation of radiant cooling or heating is to embed the water tubing in the floor structure itself. Most of the time, this is accomplished by laying out the tubing in a grid, then pouring the concrete flooring over the top of it. By flowing cold or hot water through these tubes, you can vary the temperature of this floor mass and cool or heat the occupants through radiant heat transfer. Again, a dedicated air system is used for ventilation and dehumidification. So before moving on to other parts of the system, Mick's going to discuss some ASHRAE standard 90.1 requirements that affect these types of terminal units.
Thanks, John. So let's talk about how ASHRAE 90.1 affects your designs with respect to economizers and fan power. The first question we have to ask is, which version interests you? Well, that depends on your location. As shown here, the vast majority of states have energy codes at least as stringent as 90.1 2007. Some have updated to the 2010 version, and others are considering local codes based on 90.1 2013. So we'll give information on all three versions. Let's start with the Economizer requirements. 90.1 has a number of climate zones. Shown are the climate zones within the continental United States. Climate Zone 7 is cold, for example, northern Minnesota, while Climate Zone 1 is the very tip of Florida. Those zones are also segregated by humidity. A is moist, B is dry, and C is marine and found along the U.S. West Coast. Take note of Climate Zones 4 and South, starting from the yellow band down. This is much of the mid-south and southeastern United States. Here's the verbiage from 90.1. Economizers are required for each system that has a fan and is cooling, but there are exceptions. The one we'll discuss today is Exception A, which refers to individual fan cooling units below a specific capacity. In a minute, we'll look at how those capacities change in different versions of 90.1. So, with respect to terminal unit systems, what comprises an individual fan cooling unit? Clearly, a fan coil or blower coil falls into this bucket. But how about passive chilled beams or radiant cooling? At this point, no. The reason is that those units do not have airflow or fans. But how about active chilled beams? This is a little fuzzier since the individual unit, that is the chilled beam, doesn't have a fan. Now, after communicating with individuals on the 90.1 committee, it seems that active chilled beams would likely be treated the same as fan coils, although that has not been officially stated by the 90.1 committee. Now, there was one public review addendum that addressed such systems, but it hasn't been out for a second public review yet. So, let's look now at the capacities below which an economizer is not required in the different versions of 90.1. If your code is based on the 2007 versions, economizers are not required in climate zones 1 through 4 and humid zones. As mentioned earlier, this is primarily the southeastern United States. Otherwise, The threshold varies by climate zone and is either 65 or 135 MBH. Moving on to 90.1 2010 and 13, as long as an individual fan coil cooling unit has a capacity less than 54,000 BTUs per hour, an economizer is not required. So if a fan coil's capacity is above that shown in the table, an economizer is required, and the economizer may either be air or water cooled. Now, let's look at an example. Unlike the other terminal unit options, fan coils may be selected to provide either sensible and latent cooling or only sensible cooling. If a fan coil is delivering only sensible cooling, how much airflow could it deliver prior to triggering the economizer requirement? The equation for sensible cooling is shown. If the supply air leaves the fan coil at 55 degrees and the space is at 75, this is a 20-degree delta T. Using the 90.1 2013 threshold of 54,000 BTUs per hour, as long as the fan coil delivers less than 2,448 CFM, no economizer is required. Most fan coils are under this limit, although some blower coils might exceed this threshold. Let's move on to the 90.1 fan power requirements. All three versions of the standard have the same fan power requirements, shown here. One thing to note is that the 2010 and 2013 versions explicitly state that single-zone VAV systems, such as fan coil with an ECM, must meet the constant volume fan power allowances, which are more stringent. A question that is often asked concerns allocation of dedicated outdoor air units or exhaust fans to terminal unit systems. For those systems without terminal fan power, the calculation is pretty simple. Does the supply plus return fan or exhaust fan power divided by the central unit's airflow meet the fan power requirement? But how does the central fan power apply to systems with fans in the terminal units? You allocate the central fan power to the terminal units on a CFM-weighted basis to determine if the system complies. The 90.1 User's Manual works through examples of the math.
As I mentioned earlier, for most chilled water terminal systems, the outdoor air required for ventilation is typically delivered by a separate dedicated outdoor air system. Next, John is going to discuss this part of the system further. John?
After the outdoor air is conditioned by the dedicated outdoor air unit, there are various ways to deliver this conditioned air to the individual zones. I'll start with a fan coil system to explain these different configurations. First, the outdoor air can be ducted directly to each zone, as depicted here. The fan coil cools or heats only recirculated air. Or the outdoor air can be ducted to the intake of each local unit, where it mixes with recirculated air from the zone. As an alternative, the conditioned outdoor air can be ducted to the supply side of each terminal unit, like here. Again, the fan coil needs only to cool recirculated air in this point in time. And finally, some engineers design the system to discharge the conditioned air into the ceiling plenum near each terminal unit. Now, each of these configurations has its own advantages and drawbacks. We don't have time during this program to discuss them, so I've included supplemental slides in your handouts. But when fan coils are used, I think the best choice is to deliver the conditioned outdoor air directly to each zone. Since the outdoor air is not distributed through this local fan, this fan can operate with a 2-speed motor or a variable speed motor, or even cycle up without impacting how much outdoor air is delivered. So you can get all the energy-saving benefits of single-zone VAV control that Eve described earlier, and still get proper ventilation as this terminal fan speed changes. In addition, this direct-to-zone approach affords the opportunity to deliver this outdoor air at a cold temperature rather than reheated to neutral. Many dedicated outdoor air systems are designed to dehumidify the outdoor air and then reheat it to approximately space temperatures, which is sometimes referred to as space neutral. In this example, the dedicated outdoor unit dehumidifies 450 CFM of outdoor air down to a 52-degree dew point and then reheats this air to a 71-degree dry bulb. The local fan coil is then used to remove the space sensible cooling load. In this example, the fan coil cools 1,380 CFM down about 55 degrees to remove the space sensible cooling load of 2.4 tons. However, when a chilled water or refrigerant coil is used to dehumidify the outdoor air, a byproduct of that dehumidification process is sensible cooling. The dry bulb temperature of the air leaving the coil is colder than the space. If this dehumidified air is then reheated, some of the sensible cooling performed by the dedicated outdoor air unit is wasted. If a space needs cooling, why not make use of the sensible cooling already done by the dedicated unit? The alternative is to dehumidify the outdoor air, but then deliver it cold, that is, not reheated. Using the same example, if this 52-degree air is delivered directly to the space, it removes part of the sensible cooling load in that space. This means that the local fan coil can be sized for less airflow and less cooling capacity than in a neutral air system. In our example, the fan coil now only needs to cool 930 CFM of recirculated air with a capacity of 1.6 tons. This is compared to 1,380 CFM and 2.4 tons for the neutral air system. That's a 33% reduction in the fan coil capacity. Looking at it schematically, when this outdoor air is delivered to the space at 52 degrees, it removes part of the sensible cooling load in that space. This means that the fan coil can be sized for less airflow and less cooling capacity, 930 CFM in this example. However, if the dehumidified outdoor air is reheated to 71 degrees, it removes very little of the space sensible cooling load. So the fan coil will need to be larger, 1,380 CFM in this case. The result is more overall airflow, more fan energy, and more cooling energy. The dedicated outdoor air unit delivers the same airflow in either case, but the fan coil in the neutral air system needs to move more air. So delivering the air cold can reduce installed costs by allowing the fan coils to be downsized, and also offers energy-saving benefits. Now, I discuss these benefits in more detail during the 2012 E&L program on water source heat pump systems. It's listed in bibliography if you want to learn more. In many cases, systems are designed to deliver neutral temperature air because the designer is concerned about overcooling. As the space sensible cooling load decreases, this cold outdoor air might provide more cooling than the space requires. As a result, the space temperature can drop. So what do you do? Well, first, consider implementing demand control ventilation. By reducing the outdoor airflow delivered to the space when there are less people in the space, you may avoid this overcooling altogether. And this saves central fan energy and the energy required to cool or heat the outdoor air. In this example, VAV terminals are used to the outdoor system. This allows ventilation to be measured and varied based on a CO2 sensor, time of day schedule in the building automation, or a simple occupancy sensor. Another option to prevent overcooling is to reheat the dehumidified outdoor air centrally using recovered energy. In this case, design the system to deliver this air cold and then reheat only when needed to avoid overcooling the zones. For example, building automation system can monitor the temperature in every zone served by this dedicated outdoor system and look for that one zone that's most at risk of overcooling, which is closest to the heating set point. Based on the signal from the BAS, the dedicated outdoor unit then reheats this air just enough to prevent the coldest space from overcooling. So there are more efficient ways to address the concern about overcooling rather than using neutral air all year long. Now, for some applications, like hotel guest rooms and dormitories, where the sensible loads are often drastically different in various spaces, there may be more hours when cooling can occur. For these applications, it might just be simpler to deliver the dehumidified air at a neutral temperature. Or if an application has very high space latent loads or requires a lower than normal space dew point, the outdoor air may need to be dehumidified to a very low dew point. In this case, the air temperature leaving the coil may be colder than the HVAC design engineer is willing to discharge directly into an occupied space. So the dehumidified outdoor air might be reheated to a more traditional supplier temperature, such as 55 degrees, but certainly not reheated all the way to neutral. Finally, if the conditioned outdoor air will be delivered to an open ceiling plenum near the intake of each local unit, that dehumidified air might need to be reheated to avoid condensation. In this case, it's a good idea to reheat the air to a dry bulb temperature that's well above the expected dew point in that ceiling plenum.
John, since you mentioned demand-controlled ventilation, let me jump in here and share how 90.1 treats DCV. Demand-controlled ventilation became more stringent in the 2013 version. For example, it likely applies to classrooms since the threshold is now 25 people per 1,000 square feet. For any version of the standard, once its people density threshold is met, DCV is required if one of the following is true. The system has an airside economizer, or the system automatically modulates control of outdoor air, or the design outdoor airflow is greater than 3,000 CFM. The last two, B and C, may apply to any terminal unit system used in combination with a dedicated outdoor air system. Also, in many cases, the dedicated outdoor air unit may be required to have energy recovery. Let's look at that. In 90.1 2007, airside energy recovery was only required in the humid climates up to 6 and dry climates up to climate zone 4. And also, when outdoor airflow was 5,000 CFM or greater and 70% outdoor air or greater. In the newer versions of 90.1, airside energy recovery is required in a lot more situations. The 2010 requirement is based on climate zone, percent outdoor air, and design fan airflow rate. Some systems as low as 30% OA require energy recovery, and in some cases, such as very cold climates, for any amount of outdoor airflow. In 2013, the threshold is as low as 10% design OA, and there are two tables, one based on operating hours less than 8,000. The second table is for greater than or equal to 8,000 operational hours. In all versions of the standard, there are a number of exceptions. Now, more specific energy recovery information is available in slides from your local coordinator. Suffice it to say that in the more recent versions of 90.1, energy recovery is required for many more systems.
Let's move on to the other types of terminal units. Earlier we explained the differences between passive and active chill beams, fan power terminals with sensible cooling coils, radiant panels, or radiant cooling using the building mass. But one common characteristic is that they all provide only sensible cooling, no dehumidification. The separate air system is used to dehumidify the space and control the indoor dew point so it's below the surface temperature of these terminal units. This avoids moisture condensing on the cold heat exchanger surfaces and dripping into the space. Typically, the air system is designed to maintain about a 55-degree indoor dew point. And then the chilled water temperature supplied to these terminal units is controlled to a few degrees above this indoor dew point, typically somewhere between 57 and 60 degrees. In addition to these other types of terminal units, some engineers use conventional fan coils in this manner too, by selecting them with a warmer water temperature that results in a sensible cooling only, so that coils operate dry. Now, for systems that use either passive chill beams, radiant cooling, or fan coils or fan power terminals with sensible only cooling coils, the outdoor air system has two functions. First, it must deliver at least the minimum amount of outdoor air required for ventilation by the building code. And second, it must deliver this air dry enough to offset the latent load in each zone and maintain the indoor dew point at or below the desired limit, which we'll assume is a 55-degree dew point. It's important to note that the quantity of air required for dehumidification depends on how dry that air is. If the air is delivered drier, that is, as a lower dew point, then less airflow is needed to offset a given latent load. Let's use an example 1,000 square foot office space to demonstrate the impact of these two functions. The calculations for this example are all included in your handout if you want to review them later. First, if I use the default occupant density, then the minimum outdoor airflow required for ventilation in this office space is 85 CFM, according to the 2010 version of ASHRAE Standard 62.1. As a side, if the project is seeking LEED certification, some design teams will choose to go after the increased ventilation credit. To earn that 1 point, the zone outdoor airflow would need to be 30% higher than the standard 62 requirement, which in this case equals 110 CFM. Next, let's look at the airflow required for dehumidification. To control the indoor dew point to 55 means that the airflow must be dehumidified to a dew point that's drier than this. Of course, how dry that air must be depends on the quantity of air delivered, as well as the latent load in that space. For this example, I'm assuming that the only latent load in this office space is from people. And the ASHRAE handbook suggests a latent load of 200 BTUs per hour per person for this type of space. So if we only deliver 85 CFM to this space, which is the minimum required for ventilation, it needs to be dehumidified to a 47-degree dew point in order to offset the space latent load and maintain the indoor dew point at 55. However, if we increase the airflow, then the air doesn't need to be dehumidified as much. At 110 CFM, we only need 49-degree dew point air. If we increase to 360 CFM, we can do it with a 53-degree dew point. Of course, this all impacts your system design. If you only want your air system to dehumidify to a 53-degree dew point, you'll need to deliver a lot more airflow than the minimum required by ASHRAE 62. This impacts fan energy, duct sizes, and if you choose to keep this 100% outdoor air, it can also increase the energy used to cool, dehumidify, or heat that additional amount of outdoor air. Alternatively, you can design the air system to deliver drier air and keep this airflow as close to the ventilation requirement as possible. Eve's going to show us one way of doing this.
One effective approach for dehumidifying this air to these lower dew points is to use a Type 3 desiccant dehumidification wheel in series with the cooling coil. At Trane, we call this configuration CDQ. This particular air handler configuration also includes the total energy wheel to precondition the outdoor air before it enters the building via exhaust air energy recovery. The outdoor air passes through the regeneration side of the desiccant wheel, through the cooling coil, and then finally through the process side of the wheel. This desiccant absorbs water vapor from the air downstream of the coil, enabling the system to deliver the air at a lower dew point without having to subcool the air using the cooling coil. When this wheel rotates, it releases this absorbed water vapor back into the air, but upstream of the cooling coil, allowing this coil to then remove it via condensation. Unlike a traditional desiccant dehumidification system, this Type 3 desiccant wheel transfers water vapor without the need to add regeneration heat at most operating conditions.
This cycle chart shows the performance of this dual wheel unit. The desiccant absorbs water vapor from the saturated air leaving the cooling coil, dehumidifying the leaving air to a dew point of 47 degrees. Now, sensible heat added by this absorption process does raise the dry bulb temperature up to 57 degrees in this case. Now, after the outdoor air passes through the total energy wheel, it enters the regeneration side of the desiccant wheel, where the water vapor that was absorbed from downstream of the coil is now released from the desiccant, resulting in more humid air entering that cooling coil. So for our example, the Type 3 desiccant wheel allowed us to deliver 47-degree dew point air, which means that the air system can be sized to deliver just the minimum 85 CFM required for ventilation. Now, if you wanted to deliver these same conditions using a traditional cool and reheat system, the cooling coil would need to cool the air to nearly 47 degrees to achieve that same 47-degree dew point. Then a reheat coil must raise that air to 57 degrees. By contrast, this dual wheel unit configuration can deliver the same 47-degree dew point air using fewer tons less or no reheat, and with a warmer leaving coil temperature, 53 versus 47 degrees. This warmer coil temperature allows for more efficient mechanical cooling. Of course, the desiccant wheel adds pressure drop, which requires more fan power. Staying with the same cool and reheat system on the right, if the building doesn't have cold enough water, and you only want to dehumidify to a 53-degree dew point, then the system needs to deliver 360 CFM to dehumidify the space, which means larger ducts and more fan power. Note that rather than condition all this excess outdoor air, in this case, I'm now mixing recirculated air with the minimum 85 CFM of outdoor air required to deliver the total of 360 CFM. Now, even though this higher CFM of air doesn't need to be dehumidified to as low a dew point, the fact that the coil needs to dehumidify about 4 times more air results in more tons at the air handler, but less reheat. Delivering more air to the space does offset a larger portion of the space sensible cooling load, so the chilled beams, radiant panels, or local terminal coils can be smaller. So you can see that there are some interesting trade-offs involved when designing the air system for these types of terminals. In general, I think that delivering the air drier and keeping the CFM as close to the ventilation requirement as possible usually makes the most sense. Let's stay with the same example office space, but look at what happens if we use active chilled beams in the space instead. The air system still has the same 2 functions of ventilation and dehumidification. But with active beams, this airflow serves an additional function. It needs to drive the induction process and draw room air up through the local coils to offset the sensible load in the space. For active chill beams, this air is typically called primary air. And the amount of air being induced up through these coils is direct correlation to the amount of primary air shooting out these nozzles. So the higher the sensible cooling load in the space, the more primary air will be delivered to this beam. More primary air passing through these nozzles means that more room air will be induced through these coils, which results in greater cooling capacity. Now for my example, I used a typical sensible cooling load for an office space, 19,500 BTUs per hour. As a benchmark, if you were cooling this space with an all-air system supplying 55 degrees, this load would require about 900 CFM, which equates to 0.9 CFM per square foot. At this point, I use catalog performance data from a manufacturer to determine how much air is needed to offset this load. Now, if the primary air is delivered at a dry bulb temperature of 55 degrees, about 360 CFM of primary air is required to induce sufficient room air through the beams and offset this sensible cooling load. Or, if the primary air is delivered at a neutral temperature of 70 degrees, then 500 CFM of primary air would be required to offset the load. Now, this is an important distinction. Some primary air systems are designed to dehumidify the air to a sufficiently low dew point and then reheat this air to a neutral dry bulb temperature. As I mentioned earlier, usually this is done because the designer is concerned that delivering the air at a cold temperature will overcool the space at low loads. But the result of this decision is that now nearly the entire space cooling load must be offset by the chilled beams, since the primary air provides little or no cooling effect. In this example, when the 360 CFM of primary air is delivered at 55 degrees, this air passing through the nozzles offsets some of the sensible cooling load in the space by itself. In this case, it offsets 40% of that load, so the beams need only offset the remaining 60%. However, when the primary air is delivered at 70 degrees, it offsets a much smaller portion of the space sensible cooling load. The impact is that additional beams are now required to provide additional capacity. And more beams means that more primary airflow is needed to drive the induction process through those beams. And since more of the cooling load is being offset by the local coils, the water flow rate is also higher.
Hey Murph, the comparison you just did suggests minimizing zone sensible cooling load is really important. Reducing solar heat gain, heat conducted through the building envelope, and heat from lighting and equipment is essential for any efficient building. But it's even more crucial when chilled beams are used to keep the cost manageable.
Exactly. The higher the space cooling load, the more beams will be needed, which means more primary airflow and more water flow. But not just installed cost, also energy use. More primary airflow means higher fan energy and more tons to cool and dehumidify that additional amount of air. And more water flow means higher pumping energy. So delivering neutral temperature air all the time has a significant impact on the installed cost of this system. More beams, larger ductwork and fans, larger pipes and pumps. But it also impacts energy use. More fan and pumping energy, plus more cooling energy. So if you're concerned about overcooling a space at low loads, rather than delivering the neutral temperature air all year round, consider resetting that primary air temperature. If you have a building automation system, you can monitor the zone temperatures and see exactly when that worst case zone is at risk of overcooling. Then go ahead and reset the primary air temperature upward. Of course, if you have a single air handling unit serving many zones with very different load patterns, reset can be more challenging. In that case, a better solution might be to install a heating coil in the duct upstream of each zone or group of similar zones. Then the primary air can be delivered at a cold temperature whenever any zone needs cooling and tempered just enough for those zones that are at risk of overcooling. Of course, there is a cost to installing these coils, but that can likely be offset somewhat by the installed cost savings from delivering the primary air cold. And if you use VAV boxes here, they provide you the added energy saving benefit of being able to shut off an individual zone or area when it's not in use. Plus, they could also enable you to implement demand control ventilation for further energy savings.
Another common characteristic is that all these styles of terminal units are connected to a common chilled water system. Next, Mick is going to discuss that part of the system. Mick?
Thanks, Jeannie. So, with all that background information, how might we design the chilled water system? We'll look at two different configurations for a single chiller system, then examine a dual temperature system. We'll finish by sharing a method that provides improved redundancy in a dual temperature system. Let's start with a simple single chiller system supplying one temperature to all units. The chilled water must be cold enough to sufficiently dehumidify the ventilation air. Note that this temperature water is likely to result in condensation in the terminal units. So this configuration is only applicable to units that can accommodate condensation, such as fan coil systems. As mentioned previously, in such a system, the fan coils can provide both sensible and latent energy removal. This configuration also allows humidity control even if no ventilation is occurring, for example, in a school during the summer. From the chilled water standpoint, this system is simple. So where do 90.1 pumping requirements come into play? 90.1 requires variable flow once pump power is above 10 horsepower. Let's look at a chilled water system design example. Design tonnage is 180 tons, and there's a 13-degree delta T. This yields 330 GPM. For this example, we assumed a system design pressure drop of 75 feet of head and a pump efficiency of 70%. This yields a pump power of 8.9 horsepower, which is below the 90.1 threshold at which variable flow is required. However, the customer has been sold on variable flow, so the system is designed for variable primary flow anyway. So in this case, the engineer went beyond the minimum requirements of 90.1. Chillers have minimum evaporator flow rate requirements to ensure good heat transfer and controllability. In this case, the minimum chiller flow sensing is based on a differential pressure sensor across the evaporator bundle. As the coil flow varies, the bypass valve is controlled to maintain that chiller's minimum flow rate requirement. Control of the pump VFD is dependent on the terminal unit valve type. Modulating valves are becoming more prevalent and allow the pump VSD to be controlled to maintain the valve requiring the most pressure, the critical valve, nearly wide open. This is referred to as pump pressure optimization and has been covered in several previous E&Ls. If there are two position valves, you really can't use valve position, and the VSD is controlled using a differential pressure sensor at the most remote control valve. This results in a system configuration and controls as shown here. So how could we put together a system with sensible only terminal units? Such a system applies to any of the terminal units discussed, including fan coils. A single chiller produces only one supply water temperature. This water needs to be cold enough to sufficiently dehumidify the ventilation air. In this case, 42-degree water is used, and outdoor air coils are selected to produce a 14-degree delta T. However, this supply water temperature is too cold to allow the terminal units to provide sensible only cooling. So return water from those terminal units is blended with the cold supply water, in this case, to supply 57-degree water. The result is 64-degree water leaving the terminal units. Some of it is blended with cold water. The rest is mixed with the return water from the ventilation air handling coils. The result at the chiller is an 18-degree delta T, which lines up well with the recommendations of the ASHRAE Green Guide. Now, let's consider how to control the two sets of pumps in this system. The terminal system pump operates to maintain either a differential pressure set point or valve position of only the terminal units. How about the central pump? The central pump must provide enough pressure to satisfy the ventilation units and to produce the required terminal system chilled water temperature. So the central pump VSD control is based on the most open valve, but only the ventilation units and terminal system temperature control valves are used. So the system is ready to go, right? Well, not if we weren't careful in our chiller selection. Here are two air-cooled chillers selected for this duty. The only difference between the two selections is the number of evaporator water passes, 2 or 3. For the 2-pass evaporator, the minimum and design flow rates are almost the same. So the system must function with essentially constant flow rate, even though it was intended to be variable primary flow. In this case, the 2-pass evaporator is not a good fit for this high delta T, low flow system design that is supposed to be variable flow. A better option here is to select a chiller with a 3-pass evaporator. Flow rate can be reduced from design and pumping energy can be saved. Now, some might point out that the flow rate can only be turned down 36%. But using the pump laws, pump power is reduced by almost 75% by that point. So a 3-pass evaporator is a really good compromise. In addition, note that the 3-pass chiller selection is more efficient, so that's an additional benefit. Now that flow rate can be varied, should we vary it or use chilled water temperature reset? Which saves more is project dependent. If you decide to use chilled water reset and all the valves are modulating, you can use valve position to reset the chilled water temperature upward. Now, some may have concerns about losing humidity control of the ventilation units if the water gets too warm. The good news is that this control is really self-regulating. As long as the coil can produce the needed leaving air temperature, by definition, it is providing the proper dehumidification. Humidity control is compromised only if the coil cannot produce the leaving air temperature. But at that point, the valve would be wide open, so the control system will have reset the chilled water temperature back down in response. Now, you may also consider a hybrid control, that is reducing both pump speed and supply water temperature. Here's a way this can be accomplished. We save pump energy by reducing pump speed in response to valve position, for example, to 70% speed. By that point, most of the pump energy that can be saved has been. Next, keep the pump at 70% speed and reset the chilled water temperature upward if the valves are still too closed. This works very well with our 3-pass chiller selection and is still relatively simple. Now let's examine a dual chiller system. The 2 chillers could be put in a parallel configuration. For this example, we doubled the system size to 360 tons. 2 nominal 200-ton chillers in this configuration could provide a total of 390 tons. So we're a little over capacity. But smaller chillers would give us no safety factor. Alternately, if the evaporators are piped in series, we can still exceed the required capacity of 360 tons by selecting 2 smaller chillers, 185 nominal tons each. This is because the upstream chiller operates at a higher chilled water temperature. In that position, it is both more efficient and provides greater capacity. So the design provides lower installed cost and higher efficiency. That's a good deal. As discussed on previous E&Ls, series chillers also simplify sequencing for a variable primary flow system. Now, what other options are available to make the system more efficient? If the system is water-cooled, a water economizer may be added. The economizer sends cool tower water through a heat exchanger and reduces the terminal unit chilled water return temperature. Since the return water temperature in the terminal system is quite warm, in this case 64 degrees, the water side economizer can reduce or eliminate terminal unit chilled water requirement at drier outdoor air conditions. Let's look at this more closely. Now, we highly suggest that the heat exchanger be piped on the return side of the system as shown. In this position, the return water temperature is warmest. So the heat exchanger is more effective and able to reduce the chilled water load anytime the tower water is cool enough. This offers more hours of operation. In this position, as long as the heat exchanger can reduce the return water temperature, the economizer is beneficial. Often the heat exchanger will have an approach temperature of 2 degrees. So as long as the tower can produce 61-degree water, the load on the chillers can be reduced. Some point out that in this position, the economizer can only reduce the terminal unit load. So how about the chilled water load on the ventilation units? In many locations, by the time the cooling tower can produce 60-degree water, the outdoor air wet bulb will be low enough so the ventilation unit load will have also been reduced. Now, what other efficiency opportunities are available? Many people point out the fact that we only need cool water for the terminal unit system. So if there were a way to produce that cool but not cold water, separately, the chiller efficiency would rise. So let's investigate the production of both cold and cool water. From a conceptual standpoint, the easiest way to do this is to separate the loops. The terminal system operates at elevated conditions. In our example, 57 degrees. This allows its chiller to operate more efficiently. So we have a good comparison of how the unit efficiency and capacity are affected by elevated temperature. Let's make the ventilation system and the terminal unit system 180 tons each. As shown here, at the higher chilled water temperature, the chiller is physically smaller and has higher efficiency. So separating chilled water loops reduces installed cost and increases efficiency. However, if the piping is separated, there's no redundancy unless a chiller is added to each loop, and that's pricey. In response to requests for redundancy, some designers have added one additional chiller and piped the systems so that chiller can serve either the ventilation or terminal system. Let's look at such a configuration. The redundant chiller, shown here as number 3, is placed in parallel between the other two chillers, and valves and pipes are included so the chiller can serve either system. The redundant chiller must be sized for the larger of the two system capacities and for the coldest chilled water temperature, in this case, 42 degrees. So let's look at how this works if the ventilation unit chiller is being serviced. To satisfy the ventilation load, the proper valves are open and closed, chiller 3 is enabled, and a 42-degree set point is used. Alternatively, different valves can be opened and closed, and the chiller 3's leaving water temperature control can be set to provide 57 degrees to satisfy the terminal loads. To summarize, a single temperature system can be used if the terminal units are fan coils. Any sensible cooling terminal units may be used with a dual temperature system. Consider piping the chillers in series if the system delta T is 14 degrees or larger. Chiller cost is likely to be lower and the system efficiency higher. Finally, if you design two separate loops at different supply water temperatures, a single additional chiller can provide redundancy. Jeannie, what do you have for us next?
Thanks, Mick. Today we talked about several aspects related to the design and control of systems that use various types of chilled water terminal equipment, from fan coils to chilled beams and radiant cooling. Now, there are a number of publications available that provide more information on the material covered today. A bibliography detailing these resources is included in your handout. Plus, we are finishing up on a new application manual on these systems that should be published early next year. Additionally, all past broadcasts are available on DVD at trane.com/ENL. All are accredited for continuing education, and many are available on demand free of charge. Visit trane.com/continuing education for a complete list to satisfy credentialing requirements, and many are lead specific. Remember to fill out a survey and let us know how we're doing. And AIA members, please remember to turn in your member information to your local site coordinator. And finally, please ask your local host about details for the 2015 Engineers Newsletter Live programs. Next year, we're going to develop 4 ENLs. Early in the year, we'll discuss variable speed compressors on chillers, and based on your feedback, we'll revisit a couple fundamental ENLs and present a discussion on coil selection and how to evaluate sound data. These 2 will be a bit shorter, hopefully making them easier to attend. And then we'll return in fall to discuss small chilled water systems. So please plan to join us. Thanks for your time today. We look forward to seeing you next year.